Hello. It looks like Matthew was trying to do a live countdown, but I'm pretty sure the auto spam limitations on YouTube are stopping him from actually completing his countdown, and I've already started the lecture. So, good morning or good afternoon, everyone. Depends on where you are. Here we are at final um, the final lecture for COMP1511 for term 2 in 2020. Lang, did you just say waking? Oh my god. The quarantine sleep cycles have indeed turned upside down. Oh, the lecturer is here. Hello. Okay. So today, actually, let's talk about what we covered last time. Do everything in the order we do things. I do like I do like that my lectures can have a kind of a ritual to them, that we always have the same kind of things. And especially if I accidentally screw up with my modifying the lecture slides, and this one here says what did we cover yesterday, when we don't actually have days in a row for our lectures. Okay. So last lecture, if you missed it, it's probably something that I would look into, is the exam format. And so we looked at all the different questions, what's likely to be in the exam, and nearly, not perfect, but nearly exact details on the level of difficulty of what's going to be there. Also a little bit of how we're actually going to be doing submission and auto tests and things like that, communication lines via the special exam email address, which we will have people monitoring, not the entire 24 hours, because we can't really have our staff working from really weird hours. Having said that, as some of our sleep cycles have also gone into strange places, we're probably going to be monitoring still up to about 3 or 4 a.m. Australian time. That's probably my shift. I tend to take the weird shifts like that. Yeah, so if you want any information about the exam, it's go back to the previous lecture. I've uploaded that to Echo 360 as well, so it's available everywhere where the course is. Today we are going to try to cover the entire course. I'm going to try to do a recap of the entire course very, very fast, because there's no way that we can cover the entirety of COMP1511 in 2 hours, but I'm going to attempt it. I was supposed to cover at least some of it in the previous lecture, but I figured people had questions about the exam, and I think it was more important for me to clarify the questions people had about the exam. So now, yes, as Leon said, we're going to speedrun COMP1511. So I'm just going to launch straight into it. Like, usually I will talk about things a little bit before we launch into the content, but today I'm just going to launch straight into the content. So, question: what did we learn this term? Answer: all the things. We're obviously going to be more specific than all the things. So let's look at what we've been thinking about. So we've been learning about programming in C, and so we're not just learning about the language C, but we're learning about programming in general. So we're learning about a lot of the things that make up how we think about solving problems with computers, and then we've implemented a lot of them in C. Sorry, someone's just standing right here on my lap, so I figured you could get a nice little look at my little buddy here. We've been learning how to pass auto tests. Okay, so what I should say about the memes in the lecture today: all of these memes were submitted by students. So I had a bunch of students who decided they would email me with more memes for my lectures, and so I just dumped all of them into this final recap lecture. So write the world hello world using C, and this is a hilarious joke. Okay, let me just move that out of the way. Okay, these are the concepts in the order that we taught them. So if you wanted to If you wanted to look at separating the course into its individual mini topics and stuff like that, then this would be the way to do it. I'm gonna put it back up to me. I think it's more important you see my face than just watch chicken and hear my voice the whole lecture. But she's there. She's there a little bit. Okay, so we're gonna go through these one at a time, and we're gonna talk about first C as a programming language. So we can think of C as a compiled language. That means we use an actual program which is called a compiler. DCC is the one that we used in the course. There are others. Clang is the one that you will get by default, I think. I'm pretty sure you get this one by default if you're working on a Mac. In C, GCC is available in most versions of Linux. Windows doesn't necessarily have a C compiler it uses on its own, but I think that if you're using Visual Studio Code, I can't remember because I've used the big heavyweight Visual Studio more than Visual Studio Code, but I know it has its own compiler as well. Well, at least it used to. So the compilers are going to read the code, and they're going to read what you've written, and then they're going to translate what you've written into code that the computer can understand, in a sense. Well, it's kind of not code anymore. It's like they call it machine code a lot of the time. So actual instructions that your CPU can just run. And it will run that. All of our C programs will have a main function in it. We've seen how to put main functions in different files. We've seen how to put main functions with arguments for command line arguments or without. And our C compiler is going to be able to compile all those different types of projects, as we've seen, because every project that we've done, either in lectures or labs or anything, we've compiled all of them. Like, we've never shown you any code that we didn't at least try to compile, debug, and run, or anything like that. So we would compile all of the C files that are in a project, but we don't compile the H files directly. We will use #include to include the H files. So now that we've hit a point where we can understand the larger context of C, I don't need to tell you the simple things about what C is as a programming language. The first time I introduced it to you, I introduced it in a very simplistic fashion. Now I can talk about all these other things because we've been through them. So C in compilation. I do enjoy this meme because honestly I get a little bit of fear as well every time my code compiles first go. Because if my code compiles first go, I just assume that I've made mistakes. Like, I don't ever assume that I haven't made mistakes. But if it compiles first go, I assume that my mistakes are buried somewhere in it. Okay, one of the very first things we did was input and output. We looked at scanf and printf. This was our capability of scanning or printing text to or from the terminal where we expect there to be human on the other end. So this is us displaying information to a person and then getting information back. So we've got our scanf and printf. We know more about this now than we did when we first used it. We know that scanf and printf are functions. We know that they're functions that have come from a library that we've included. So in the very beginning when I showed you this, I said there are other lines of code here. Please ignore them. We'll talk about them later. Now that we have talked about them, you know, right? So we know that these are functions we've taken from a library that we included, standard input-output library. We know now that this AND here is a memory address, which means that scanf was receiving a pointer to a memory location where it was going to write information that it received from the terminal input. Right? So scanf is very different now from how I explained it the first time. Now you know that it's a function that takes a pointer that writes something into memory. So we start to think about these things a lot differently now. But we do know that there's lots of different pattern strings that we can use to scanf different kinds of information and interpret that information in a way that we want to be able to use it. We have lots of other ways to do input and output if we want to. If we want to scan or input one letter at a time, we can use getchar and putchar to grab one letter at a time or place one letter at a time. This can be a bit cumbersome, but it does mean that we get every single character. So if you want to get all the spaces and the new lines, you can use something like this. Scanf is going to ignore white space, so it's just going to grab words and ignore the gaps in between them. But if you want to know the gaps in between the words, then you want to use things like these functions instead. Fgets and fputs will be able to work with entire lines, so they will take all the spaces but they will take the input in chunks. So every time you press enter, fgets will take an entire chunk of input. So different ways to work with it. We also looked at conversions. So string to long is one function that can convert characters into numbers. So it can read a string of numbers, of digits, and then interpret it as a number. What are people asking questions? Oh, I accidentally answered Quirty 11's question. Hopefully that helped. Alright, I'm not going to go too much. Actually, you know what? I think I'm going to have to ignore the questions and just go bang, 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 bang. We are speedrunning. Alright, we also looked at command line arguments. Command line arguments are another form of input into the program, but they are reading the line of text that actually runs the program. So it's like, it's not exactly the same, but it's like we ran fgets on the line before the program started running. So the actual command that runs the program. And so we have a specific format for this using the argc and argv, which is this main here, which is argc and argv. Argc is how many words were typed in the command line. So this is going to ignore white space and just have words. These words could be numbers or they could just be strings of letters. The argc and argv are not going to care whether it's a number or a letter. It's just going to store everything as strings. So here is an array of character pointers. An array of character pointers means a character pointer can be interpreted as a string if you want. So this is an array of strings. And so if we're going to go through each of these and just loop through from 0 up until the count of arguments, then print each one of them out as a string, we would get something like this. We run with the program name, this one happens to be called args, hello world, and then it will print out all of the words that were typed in on the line that ran the program. So command line arguments allow us to use information as it's given to us. Okay, so you can see how I'm going out of order. I'm not doing things in exactly the same order as we taught them. I'm now doing things in order of their relevance to each other. So variables. This is one of the most fundamental concepts of programming. It's very, very hard to do programming without some variables. It is technically possible, but very, very difficult to do programming without declaring variables from before. Yeah, Leon, we're out of order now. We're in a more logical order than we are in a teaching order. Teaching order is based on what you know and what you need to know next. Now it's like clustering I'm clustering things via subject matter. Okay, variables store information in memory. You know a lot more about memory now than you did before. You know that they are chunks of ones and zeros that store information about something. So we now have lots of different types. At the beginning, we only showed you 2 types just to make it reasonably simple to see how you're working with things, and so we're only using numbers. But now we know we've got characters, we can build our own things with structs, we can put collections of things together with arrays, and if we get really deep into it, we could consider our abstract data types and our type defs to be, in a way, variables, because they're variables that access other variables. So every variable has some kind of value that it stores that we can access and change. We can give the value of variables into functions. We can give access to a variable by giving a pointer to it and things like that. And we also looked at constants. Constants are ways for us to set up a value that won't change while the program runs, but while we're developing code, if we need to make a change, so excuse me, I am talking fast, I can feel it. If I want to set up something like the size of a board in a game, so I say I have a tic-tac-toe game, and I set up as size 3 because it's like 3 width, 3 length, 3 height, 3 width. I could say that, and then you could say, oh, can we play a harder version of this game, which is a 4x4? If we had a constant for that size, we could just flick that up to 4, and then hopefully the game would still work. I know that tic-tac-toe, a lot of the rules in tic-tac-toe won't work in 4x4, but, you know, it'll still give us a way to change a number in between compilations, in a sense, that will give us a chance to change major settings in a program without having to go through and change individual bits. So that's where we'll use constants versus variables. Variables are things that are quite a lot more volatile, and they're going to change a lot more during the running of the program itself. Okay, really, really simple variable codes here. I could define, and remember the naming scheme of how we define things. I could define Goku as 9001. If you get it, you get it. If you don't get it, Dragon Ball Z has a character called Goku, and there's a really famous line in this saying, he's over 9,000. That's why I did 9001, just for fun. Anyway, so we can define Goku here as 9001, because he's over 9,000. Then there's other ways of using variables. We can declare a variable, we can change a variable's value, we can use the value in the constant and assign that to a variable. So power here would be equal 9001. If we want to declare and initialize a variable all at once, we can declare the variable by its type and its name and then its value, so that it'll always have a value. This one here is a little bit scary because I've declared a variable, I have memory for it, but I have no value, so I don't know what this is. If I read from this variable now, I have no idea what's going to happen. Because it could be, if my compiler is nice, it'll be a specific value to let me know there's no value. If my compiler is not nice, it's just whatever had been in memory before I declared that. Someone's auto test literally has that Goku in it. Okay, then we had if statements. If statements, I like to think of these as questions and answers. So this is us being able to turn on or off parts of our code. We'll only run parts of our code if certain questions come up correct. So for example, here, very, very simple one. The question is x less than y? If x is less than y, then the section inside the curly brackets will run. Otherwise, we will skip past the closing curly bracket and then run whatever's afterwards. I think that everyone's pretty strong on if statements now. I think people are understanding them, so we probably don't have to worry too much about what's going on there. So while loops are our capability to repeat running the same code multiple times. When we're thinking about while loops, the things that we always really want to think about when we create something that's going to run multiple times is always think about how they're going to stop. So we're going to make it stop. So we need to be able to say this is either going to run a certain number of times or it's going to stop after a certain condition's met. And so I've shown you code for both of those techniques, specifically with arrays, but I've also shown you that with linked lists as well. Very, very often a loop is used to check every element in a data structure. So I consider arrays and linked lists to both be data structures because they're ways of structuring large chunks of data. We will often use loops to just look through everything in that. Or we can say keep doing something until a condition is met and then we don't have to do it anymore. Or even in the more subtle ones that we looked at, just move through the code, move through the data structure, don't do anything in particular, but stop when we find a certain condition. So when we're doing like alphabetical insertion and stuff like that. So we've got a funny meme here for looping. How do we add 50 to x? So just add 50, or add 50 with no shorthand, add 1 50 times, or add 1 50 times. Okay, let's move on. Yeah, there are for loops in the meme. I did allow that because I was given it by a student. I thought it would still be funny. Some people like using for loops because you're less likely to forget the I++, because the for loop literally tells you have to do it at the beginning. Some people prefer while loops because if you read them from top to bottom, then you see exactly what's happening in order. So there's arguments for both. I'm not gonna go back into the while loop for loop argument because I think we've had that one several times. You can end up using whatever's comfortable to you, basically. Okay, so a while loop looping through an array will have a very similar setup all the time. we'll start with a counter, and it will be set up for wherever we want to start counting from. We don't always want to start counting from 0. Sometimes we want to start counting from the other end and go backwards. Sometimes we have a reason to start counting from a different place. Whatever you need to do, you set up the number to begin with, and then you set up the limit for how far that number should go before it stops, and then you increment in whichever way you're going to increment. This is the most basic way, that starts at 0, so the very beginning of the array, goes to the end of the array, 10 there. Here we would potentially have this 10 as a hash define instead, but there's not that much space on the slide to show that. And then we could say, ooh, that code doesn't even make sense. There's no variable called counter. I'm gonna fix that. I don't know how many times I've delivered that with the incorrect code in there. So this is just saying count from 0 up to 9 and put those numbers into the array. Other code for looping through linked lists is we could have a pointer that starts at the head of the list. This can be a pointer that's given this head. So we're just assuming that somewhere before this thing starts we have a head. And then this is the first element of the list, and we say if it's not null, then we're going to do something with that element of the list. And when we're finished doing whatever we needed to do with that element, we move that current pointer onto the next node in the list. So looping through linked lists is a little bit different. We use less numbers, but we use the concept of following a trail of pointers through the nodes. Oh no, the while loop for loop argument is still happening in chat. I'm going to move on because that was the amount of time that we were going to spend on looping anyway. Okay, so arrays. Now we got to the point where we were able to loop, and so I said we're not just looping to repeat the same code over and again. We might be looping through a data structure. We've already talked about looping through arrays because you already know what arrays are, but let's talk about specifically what arrays are. When we are using multiple of the same variable, we can say, let's make a collection of these, which is an array. So here we have the idea of an array of integers. We have an index for each element in the array. So we're accessing each element in the array by a number, not by a name. The entire array has a name, and then each individual element it just has an index inside it. When we create arrays in our code, they will have a fixed size at the time that the program starts running. So at the time the program starts running, actually, I think it's even before the program starts running. Once it's compiled, your arrays are set in stone to be a certain size, and you won't be able to change them. So we would run our arrays knowing that they're always going to be a specific size. A lot of the time when we do it, we'll hash define that size so that we know that every time we use it, we know what our limits are for maximum size. Yeah, I don't think I need to say much more about that. There is some demo code here for using arrays, which is basically how to initialize. Note that the 0 here is a special form of initialization, where if you put just a 0 in here, it will set all the values of the array to 0. It doesn't actually work with any other numbers. If you want other numbers, usually you'll have to lay out all of the numbers. Each element, so remember, the square brackets are used to declare the array. When it's being created, the square brackets mean length. When it's being used, the square brackets mean which element are we looking at. So the square bracket is the symbol of the array, but that doesn't mean it has the same purpose in every line of code. So when you're creating it, it has one purpose for size, and when you're using it, it has a different purpose for accessing an individual element. Other than that, we can put anything that has an integer value inside the square brackets, and we'll be able to index something. So we've seen this before, right? In the while loop with the I, we can access certain elements of the array. I know this might have slipped from people's minds because it's been I think nearly 2 months since we actively used arrays. We've been really deep into linked list recently, but we're still going to want to know these. These are still going to be very important. They're going to get used a lot anyway. So no, it's about Sprintf makes you sprint fast. No. Tom can answer that one. Okay. Functions. Here's a lovely meme. You don't ever have to pass parameters if everything is in main. Yeah. Okay, that's how you lose all the star marks and all your stuff breaks. But anyway, okay. We learnt functions. Functions were how we wrote code that was separate to our main code, but we could use this by jumping over to the function code, running the function code, and then jumping back to our main. Or even better, jumping into a function to run some code, and from that function jumping into another function to run some code, return from that function to the previous, and then return from that function to the main. So this gave us the ability not only to reuse code, but also to be able to compartmentalize our code via its subject matter, which makes our code much easier to read. Because when you've got the main on its own, you just end up with like this huge block of code that does a million different things. It's really hard to tell where each part starts and stops. Whereas if you write a few functions that say, okay, this function does this thing only, and this other function does this thing only, then you get this situation where you can say, each one of these functions has a very specific purpose, and we use the functions for those specific purposes. And it's much easier just to organize what you're doing like that. The nitty-gritty of it, I think I've got a slide. Yeah. Every function is going to have a type, which is actually its output, and also a couple of variables declared as its input parameters. There's lots of different names for them. Parameters is one, operands is another. There's lots of names for like the stuff that goes into the function. But as long as you know that it's the stuff that goes into the function, you don't always have to know all the different names for it. So we've got a really, really simple function here that adds two numbers together. It's kind of redundant because you could just use the plus, but we just think of this as an example of how to set up a function. So we know what it does because it's got a good name, it has a comment that says what it does, it has inputs and it has an output. We use the return keyword to give its output back, which means we can say when we call this function by its name, we always need to give it two values. A value that can be used for this one and a value that can be used for this one. So we give it the value from first number, which is 4, and the value from second number, which is 6, and we say add these up, put it in total, and then we could use the total for something like that. So when we call a function, we think of the function as basically running everything it does and then transforming itself into this type when it's done. So when the function's finished, whatever is where the function was called will become an integer in a sense, and the actual value that it becomes is this a plus b here. So it should be 10 for this one. Did I not say arguments amongst all of that stuff? I said parameters, but not arguments. Yeah, see, there you go. See, there's so many names that I'll forget even one of the most obvious ones. Also, because I'm speedrunning here, I'm just like, just keep talking. All right, then we got up to pointers. And pointers is where, so the way I think of the course is you're all little chicks in the nest. Little chicks like this one. She's a different kind of chick. She's a chicken. And I'm the mama bird. So what I'm doing is I've got food and I'm regurgitating it into your mouths, right? This is like, sorry. I've obviously been talking too fast. My brain is addled, so I'm using hilarious analogies instead. So up until this point, all I've been doing is just giving you information. Then we hit pointers, and pointers is the point where Mama Bird says, you need to learn how to fly now, so I kicked you out of the nest. So you're, I don't know, like 20 meters above the ground in a tree. You don't know how to fly yet, but I have definitely just kicked you out of the nest. This is what pointers are, and then you were forced to fly. Whether you could or you couldn't at that point in time, you were forced to fly. Don't worry if some of you are still falling. That's perfectly normal. Pointers are not necessarily the kind of thing I expect everyone to get in the first month of seeing them. It's been more than a month, but only just. It's been like a month and a half since you first saw pointers. I'm more than happy for fully qualified computer scientists to take 6 months to get this concept, or even longer. I've seen people take longer than this, and they're fine. So don't worry if you're still trying to flap with this, but it's something that you will get eventually. Apologize, everyone. I don't know what it makes the tutors. Maybe the tutors are all the mama birds. Maybe I'm just some weird rooster off in the distance just yelling at the sun. Okay, so let's not continue this analogy. It doesn't make sense anymore. It didn't make sense when I started it either. Okay, so a pointer stores a memory address. So the memory address is a location somewhere in memory where we probably have variables. Sometimes we don't, but we usually wouldn't make a pointer unless we intended to aim at a variable somewhere. Whether that's a memory allocated variable, which we now know about, or whether it's a variable that's just been created as part of the code. We call them variables on the stack versus variables in allocated memory, which is also called the heap. Don't worry too much about those names. You will see them more later and you'll get familiar with them. We kind of didn't bother pushing a lot of that detail on you. But we store a memory address, which means the pointer gives us access to a piece of memory. I think I've said that. The symbols that we're going to use for these are important as well. So, the star says we're going to dereference the pointer. So the pointer is a reference to something. Dereference means we follow it to the variable it's pointing at, and then we can access that variable. So any changes we made to a pointer with a star on it allow us to change the memory that the pointer was aimed at. If we change a pointer without putting the star on it, that changes what the memory address that is stored in the pointer is looking at. I've actually got some more detail on this. I'm going to look at it later. When we go into like the deeper stuff into memory. An AND on any variable gives us the address of that variable. So if we say AND of an integer, for example, it'll tell us where in memory that integer exists. I can assign that address to a pointer. So putting an AND on a variable is nearly like making a pointer to it. So it's giving you the value that would be stored in a pointer. When we're using structs, this is the nice thing about this now in recap, because I can talk about structs, because when I first talked about pointers, I couldn't talk about structs. So the arrow says follow a pointer into a struct and look at a particular field inside that struct. So the fields inside the structs are the individual named variables inside the structs. So the arrow says we're going to go into the struct and use it. I didn't even put the dot here, actually, because the dot is something that we actually haven't used that much. I mean, it's useful to know that you can access something in... Oh, right. The reason I didn't put the dot here is because the dot has nothing to do with pointers. That's right. We'll look at that in structs. Okay, so some simple pointers code. This is the same code I think I used in my slides when I was introducing pointers for the first time. I can create a new pointer by saying... the star is the symbol of the pointer, right? So it has the same thing as the square brackets. It's got a different purpose when you're creating the pointer as to when you're using the pointer. So this is creating the pointer, we know because it's got a type. The pointer has a type and it says I point at this address. This is the address of this variable. And then we can say, we can look at the pointer as if it's a pointer and say what is the address of the pointer, and then we can look at the thing that the pointer is aiming at by putting the star back on it. So this says I'm not looking at the pointer, I'm following the pointer to a variable and looking at it there. And then I can say what's the value of the variable that the pointer is aimed at. This also allows me to do cool things like saying I can pass a pointer into a function. Previously, when I passed a variable into a function, I would not be able to make changes to the variable that was given to the function, because everything that's given to a function is a value. But if I give the value of a pointer to a function, it gives this function access to the original variable that it was created from. Okay, so that was everything that I was supposed to do last lecture. So I managed to get through it in half an hour, which is good. That's the first half of the course. It's not exactly the first half of the course, but it's pretty much, it's only the technical stuff in the first half of the course. All right, people are asking some questions there. No, it's all right. Let's keep going. Okay. So when I looked at the first half of the course, I only looked at what we learned in terms of code structures for the first half of the course, and I didn't have all of this other stuff in here, which is actually quite important, which are all of the skills we need to learn that will take us beyond the language of C and take us into our overall capability to program in general, which is kind of more important. Like, it is good to go through the crucible of fire that is learning how to program in C and do manual memory management and stuff like that. There's all that hardcore stuff, and a lot of people love that hardcore stuff. But it doesn't work that well without all of this other stuff. So if you're just really good at hardcore writing C, but you can't debug anything, then it's not going to get anywhere, right? Because you're just going to write C that has bugs and you won't be able to remove them. So we'll have a quick look through this. I think I should put my face back up there. So, problem solving. Problem solving is understanding what it is you're trying to do, understanding what is and isn't working about it, and trying to make it work. So, this is classic, right? It doesn't work, why? You make some changes, it works, why? You don't actually know if the changes you made actually make sense or not. So, this comes from us not having a complete understanding of what we're doing. Sometimes we don't have a complete understanding of the code that we've actually written. Sometimes we don't have a complete understanding of what it was we were trying to achieve when we started writing the code. So it's always a bit fiddly. And so what I was trying to teach you here is every problem, especially the ones that look too big to understand, they're usually made up of smaller problems. So if we can always have a plan to solve something, no matter how big it is, we can get a better response out of what we do. So look for ways to break things into parts. This will not only teach you about how to solve problems in general, and this will leak out of programming. So this will definitely leak out of programming, leak into the rest of your life, and you'll start seeing ways that you can crack difficult problems just in your everyday lives using the same techniques that we're learning about breaking computer programs into parts in order to understand them. And so this ties in a lot with what I was teaching you about how to use functions, right? Because a lot of the stuff about breaking stuff into parts with functions is the same thing as breaking apart a difficult problem into smaller chunks that you can think about. And then we can go, okay, how do we actually start solving a problem? We look at the easy bits, we solve the easy bits, and the solutions to the easy bits will often give us clues about how we're going to solve the harder bits. Or we'll put together small parts of things, and then once we've got these small parts, we'll find that they just interlock together really nicely, and then you get Voltron, right? So, I don't know if everyone knows about Voltron. It's like, actually, it's got a new TV series, so you probably might know about it. These separate robots, and you put them together, and it makes a bigger robot. And you have to do it, or else the episode can't end, of the TV show. The other thing that makes this really handy is each of those small parts, you can make sure that they're working individually before you piece them together. Because once you piece everything together and one part isn't working, it's really hard to tell which part's not working. So if you test things individually, it's easier to get to your end goal. We also looked at code style. Code style has a very strong correlation between how efficient you're going to be with your debugging and your kind of late code problem solving. Can often be very strongly based on how you wrote your code in the first place. So I know that it always takes longer to write code that's easier to read, but I think that it's, in the end, going to be more efficient for you to write code that's easier to read, especially if you're going to work with other people. So if you have styled your code in a way where you can see clearly everything that's going on in it, it's really easy for you to just look through it and find your problems. If you styled it in a way that's even better than you being able to understand it, that other people can understand it as well, then you start to get to the point where you can work in a team really well. And we're very, very rarely going to be working alone in programming. I apologize that the way that the subjects are set up at university for individual assessment and stuff like that means that a lot of the time you're not working in teams, which means you don't get the experience of what it's like to work in a professional sense. Having said that, there'll be plenty of group work during a degree, so that you will get to know all of the ups and downs of what it's like to work with other people. And there's ups and downs, but either way, it's always going to be the way we do things because we're more efficient in groups than we are alone. Code reviews, okay, this ties into that, right? If we're working with other people. So we tried to do a lot of these in the tutorials and labs, but I don't know how much that's actually been able to happen. We would have loved everyone to do what we call extreme programming, where everyone was working in pairs all the time in labs. So you would very often be working on a problem together with someone else, and you just bounce ideas off each other. You have one person on the keyboard while one person's doing the thinking, and so one person can be worried about syntax while the other person's worried about algorithms and high-level problem solving. And it works really well, you know, because then you just bounce off each other, and both of your code gets better from doing that. Looking at other people's code gives you a lot of insight into how other people are solving problems. It might teach you new ways of doing things that you didn't know existed. So that's why we try to keep all the lab material really open, where everyone can talk about it and they can bounce ideas off each other and things like that. Obviously can't do that for the assignments. And the weekly tests. Everything like that we're trying to do individually so that we can actually give you a mark that's your own mark. Imagine that, having your own mark. I have my own mark, it's me. But imagine everyone having their own mark. There'd be so many of me. It'd be great. Anyway. Okay, debugging. I like this meme. This is one of my favorites. Being the detective in a crime movie where you are also the murderer. Okay, the removal of bugs. We looked at two types of bugs, and when we're thinking about the kinds of errors we're going to get in our code, largely, I'm not going to say entirely because there are other ones that but you don't know about them yet. We will get into them later when you do some more difficult programming. But for the moment, most of our bugs are either going to be syntax errors, which we've just basically translated our thoughts into C or whatever language we're working in slightly incorrectly, and so we've come up with something different from what we intended. Sorry, not from what we intended. We just wrote something down that the computer wouldn't understand. Logical errors are the ones where it's different from what we intended. So we say, all right, we need to loop through this whole list, and we need to find the largest number in this list. And then you loop through the whole list and find the smallest number in the list because you've forgotten what the original task was partway through. So what we can do is we can sort of separate these into two different types, because they're going to have different sort of manifestation of results and different ways of finding them. Logical errors are usually going to compile perfectly. So you've written perfect C, you know, you've spoken C with perfect grammar. You've just asked the computer to do the wrong thing. Whereas syntax errors is you've said something that makes no sense, and the computer just kind of looks at you and goes, I don't know what you're doing there. I can't access a variable that doesn't exist, you know, something like that. So when we're debugging, similar to problem solving, is we're going to get in there and get as much information as we can. So with problem solving, we would separate things into different parts. When we're looking at specifically debugging code, I mean, we could consider debugging to be a form of problem solving. We're looking at going in and separating out our code between sections that we know work and sections that we know don't work. And we can do that sometimes by just getting more information. So just the simplest form, and it's a pretty brute force approach, but the simplest form is to put a lot of print statements in your code saying, I'm here now, I'm here now, I'm here now, and then you know where it stops, at least. As you learn more about programming, you will get much better, more subtle approaches to doing this than just going, yeah, print everything out. But having said that, some of us, as professional programmers, will still occasionally use just the print this stuff out thing, because sometimes it's easier than going into the much more complicated debugging systems. There are entire systems built around debugging code. You'll learn about them eventually. We can't necessarily teach them in 1511. But if we can separate the parts, we can isolate the code where we can see what's going on, we can find our errors. And then when we're thinking about logical errors, it's always good to go back to the questions. So if you've written down clearly in advance what you intended to do with the code, you can always go back to that and say, okay, this was my intention. How am I meeting that intention? Is it working or not? We talked about professionalism, so not everyone would have necessarily been in this lecture because this one was a week 6 special that I did as an optional lecture. It's something that's going to come up much more later than it is now. This lecture, this is why I put it in week 6, because it's not really definitely what you need to know right now. But it's about the idea about what's going to happen to you when you finish your degree and you start looking for work. Or even not finish your degree and you start looking for internships. You want to work in a professional situation. And we talked about what is it that people are looking for in workmates, in a sense that people are going to work with them. So I put together a list of things that I consider important to people. Communication, teamwork, resilience, and your technical skills. So your technical skills are still there, but these are the things that people are hiring for. Yeah, they will make sure that you have a certain level of technical skills. There's always a bar that will need to be passed, depending on the job, though. You know, because there's a lot of non-coding jobs that require a computer science degree. So sometimes your technical expertise necessary is not actually programming. It might be design. It might be requirements gathering. It might be QA testing and things like that. And they're all going to be different roles. And also like management and things like that, where a lot of times people will hire their managers out of computer science degrees because they want their managers to understand what their people are doing. They're never actually going to write any code, but we need to know that they have an understanding of how it works. So with those ideas, I boil it down to this idea that if you care about what's going on, you care about what you're doing, you care about the people around you, you're probably going to have a better time with what you're doing. It's hard to just say you should care about stuff, because generally people care about stuff via a long process of doing lots of it and being fulfilled by what it is you do. So this is always going to be a matter of choice, and this is something that will come up for you as time goes on, whether you choose to be continually fulfilled by something is whether you'll care about it. And it's like a chicken and egg thing, right? So there's chicken who's walked off that way, and I don't have any eggs here with me. But, you know, if you care about it, it's more likely that you'll be fulfilled by it. If it fulfills you, it's more likely you care about it. Hello, yes, I did say your name. Yeah. And if you care about the people around you, you're more likely to have a good time working with them. You're more likely to lift each other up, and end up in a situation where you're producing your best work. So yeah, I don't have enough time to spend on this slide. I kind of want to spend every time I get to this and that lecture, I want to spend hours and hours and hours talking to people about things. And especially, like, another thing that I talked about in that lecture was that it's not super important how good you are at everything. It's more about how good you're going to end up at things, and caring about things gives you the long-term benefit in the future versus whether you're just good at something now. Because we've got a lot of issues with ourselves, talked about imposter syndrome and stuff like that, us not quite believing in ourselves, in what we do, and I think a lot of people put too much stock in immediate success and not in future success, because you can be successful in the future if you care about what you're doing and you're willing to put the effort in eventually, regardless of how good you are at the time. Anyway, I'll move on, otherwise I'll keep talking about this forever. Whoa, I made it to the break. Okay, the speed run is going well. The speed run is going very well. I made it to the break. I know that the second half of this lecture is much, much longer than the first half, so okay. So before we go on break, before we go on our final feeding break of the year, she's right here, by the way, she's just sitting on my desk right there. I wanted to talk a little bit about the future because your time with me is very short and it's coming to an end. And so I want to leave you with things to think about that you can use in a much longer term than your time in COMP1511. So even if you can't answer these questions right away, even if you can't answer these questions with an absolute clarity, I think it's still good to ask these questions, um, and um, and try to use them to give yourself some direction with what you're doing. This actually ties into what I was saying about professionalism a second ago. So why are you doing computer science or a related field? Because I assume that if you're doing COM 1511, you're likely in a related field. The way things are nowadays, if you're living on the planet Earth, you're in a field that is relatively similar, relatively related to computer science, because computers are slowly taking over kind of everything that we do. So I know that for a lot of people, the answer is this looked interesting. I didn't know what to do out of high school, so I picked it. That's fine. You know, you don't have to say, I want to change the world via this and this, and computing is the way I'm going to do it. I want to build the next super AI, and I would like to our evil overlords to take over all of us, and I want to create them. You know, that kind of thing. Not necessary. You know, it's just a matter of you thinking about why you're doing something, and eventually reaching a point where you are doing something because it is the thing that you want to do, and it's the thing that makes you happy with your life, and so you can think of continuing doing it for many years, because it fulfills you. So, for example, it took me, I think, 10 to 15 years before I realized that I just was not that fulfilled with being an engineer, but I was much, much more fulfilled with educating people and getting people to the point where they themselves can carry on their ideas based on what I've told them, you know, and that's so much more fulfilling for me than writing code and releasing it or anything like that. And then think about, okay, maybe you do or don't know why you're there, but maybe you want to know what you want to do with the skills that you're learning. I mean, for a lot of people, this is a really simple answer. I need to eat food, and I need to have a roof over my head, which means I need to make money. So I'm going to do computer science because computer science is a reasonably reliable way to make money the way the world looks right now. Cool, that's fine. Maybe I want to do research, though. Maybe I want to push really difficult technical things. Or maybe I want to change the world. Maybe I want to use computing to bring about some kind of social change, or something like that. Your goals are your own, right? You can say, I've got these distant epic goals, or you can say, I've got these close goals that I'm working on. Either way, it's fine. So long as you have a reasonable idea about what it is you would like to do with the skills you're learning, you can then say, all right, I've got 3 years, 4 years, depending on your degree, depending on how you run your degree, 5, 6 years, like mine. You can decide how you use your time to push yourself towards your goals. So long as you think about what you want to achieve, you can say, okay, what do I need to do to get where I want to achieve? Sorry, I need to learn how to speak English before I start lecturing. How I use my time to achieve the goals I've set out for myself. And it's not always a bad idea to look back at these goals every now and then and say, am I still moving towards those goals? Or would I like to change my goals? Have I decided I would like to do something different? One of the greatest things that you're going to get out of UNSW is you're going to see a lot of different stuff. I'm going to ignore chat. I'm trying to ignore chat right now. I can see it. I'm ignoring it. If you have... Yeah, you'll see a lot of really interesting stuff. So you might see a subject and it might click with you really well. And you go, oh, I want to do that now. And you go, I'm going to change my goals. And that's fine. You know, I think it's more important to have goals that might change than it is to to not change them and hold to this like kind of like stupid consistency to things. Like, you don't have to say, because I had this goal when I started my degree, I must stick to that goal. And I don't mind if for some of you that means that you hit this point and you go, computer science is not actually what I wanted to do. Like, I was interested, COMP1511 was vaguely interesting, but it just wasn't that, it wasn't clicking with me in a way that made me want to know more about it. So you go and explore other things, right? Your goals shift and change. University is a great time to discover a lot of the worldwide knowledge available to you to be able to do things. So yeah, so I think that's worth doing. This is, you can see how this is a version of the talk I gave you in week 1, where I said that there are many options to you and they're available. But now what we're thinking about, because we've done 10 weeks of exploring very deep into one particular topic, we can start to think about, okay, does this follow the goals I have for myself? Do I want to get really, really good at programming because that's going to help me achieve the things I want to achieve with my life? And if nothing else, you can just say, I have no idea what I want to do and I don't know why I'm here. But at least you ask the question and you can say, one day I'm going to figure that out. You know, one day I'm going to figure out what I want to do, and then I'm going to aim towards it and push towards it, right? So you don't have to answers to things. So I put this note here. You don't need the answers yet, but you're at a time now where you've got a great opportunity to learn things. So directing that learning via what you want from your life, I think, is a very positive thing to do. Okay, let's go on break. And it will, yes, be a feeding break. I don't think it'll be our last feeding break for the term, because I'm going to do a live stream sometime next week, and it'll probably be an afternoon, because the afternoon sessions are pretty chill. But now we will do our last official feeding break, so I'll be right back. Oh, someone's really hungry. Someone's really hungry. Is that good? Thank you. Just watching chat at the moment. I'm not sure if you can hear. Oh, you should be able to hear me. Yeah, Liang. There's and this is a good thing to say to everyone. There's actually a reasonable chance that a lot of you, once you graduate, will be scattering over the globe. If you're in the computing industry, chances are there's a lot of work all over the place. I mean, like, even um, a lot of the computing companies in Australia are hiring people from overseas for particular expertise, and then Australians will get hired to other places. Like, there's a pretty large community of UNSW grads in Silicon Valley, you know, so there's like a huge percentage of you will end up over there. So it's not something that I think you need to worry too much about an individual country's focus on something and whether that's a good idea or not for what you want to work on. Because if you have an expertise in something and someone somewhere else in the world wants to use that expertise, they're going to support you to give you a chance to move over there. All right, I'm just going to move the camera. You happy, chicken? I think she's happy. All right, back in lecture mode. Curious Cat is asking, do you need an HD average to get a job in Silicon Valley? Sorry. I apologize for laughing at your question. I have friends who have jobs in Silicon Valley who are nowhere near an HD average. They're like so far, so far from an HD average. Okay, it's not quite like this right now. Right now, things are super messy because of COVID, but we assume that the computing industry is going to sort of balance itself out. Um, what I was told. I never went. I never went to Silicon Valley, so I actually stayed in Sydney the whole time. So this is I'm telling you about international opportunities. I stayed in Sydney, but a friend of mine who went over there and came back said that he said to me if I was bored and I wanted to, I can get a one-way ticket over there, hop off the plane, and just put my hand up and go, "Hey, I know how to code," and someone would throw a salary at me before I left the airport. I mean, he was obviously exaggerating there, but it's that kind of situation. I don't know if it's still exactly like that nowadays, but at least to a certain extent, I mean, there's a kind of like that startup culture there where everyone's trying to start up a business and there's lots of funding going into work in that area. Um, but in general, there are less software engineers. So I'm going to use the term software engineer because that's like the blanket term for kind of everyone that works in the field. The the prevailing kind of idea, and I don't know if it's true or not, but the prevailing idea was there were more jobs than there were people to fill them in general. Um, so if you were competent and could work with other people, then you can get work. Um, I don't know how we're doing with COVID at the moment, and I personally would not go to Silicon Valley right now because the the chances of dying in a global pandemic right now in Sydney versus in Silicon Valley are significantly different. So I would just be like, I'm not going to America. In fact, I don't think you're even. Oh, actually, you can go to America, but you'll never be allowed to come back if you do. I think it's along those lines. Um, but we'll see what happens when everything settles again. I'm not going to say everything goes back to normal. I don't think that that exists. I don't think the idea of normal exists. But when everything settles back to a flow where the computing industry is working kind of at full steam again, then we'll see how things go. I know I've seen a lot of current students have a few things delayed because of COVID, so they've been offered jobs, but they just can't take them yet because the company said, "Ooh, chill for a bit. I don't think we can't have you in yet, but soon." You know, so we'll see how things go as industries ramp back up again. Yeah. Um, what are we talking about in chat? Oh, Tom's saying we can't actually leave. Yeah, but you could actually even better. You could actually just stay in Australia and work in Silicon Valley at the moment. Okay. Matthew is telling me that we've burnt too much time in the break. Having said that, I think a lot of what I've been talking about here, I think, is important. Nearly more important than the actual content of the course, because I think it's like charting where you want to go in the future and things like that. But let's hit it again. So one thing that I was wanting to ask everyone to do, this will be open for I think a couple of weeks still. I can't remember if it closes before or after the exam. Unfortunately, the surveys will close before you get your results back, so you can't just give me massive negative results if you do badly in the course. But we would like everyone to fill out the course survey if you can. So you can access it via Moodle. There's a link in Moodle that goes there. Or you can go to myexperience.unsw.edu.au, and one of your options there will be a survey for 1511. A lot of what people write in the survey ends up being why the course is the way it is. So a lot of changes to the way that we assess things, and a lot of changes to like things like the structure of the weekly tests and the labs and the help sessions and all that kind of stuff have been built based on student feedback. So if we don't get feedback from people, then we don't necessarily know how to improve the course. So as many people as possible, can you please give us feedback on the course? And this doesn't have to be positive feedback, right? Like if you think that, okay, course was fine, I learned a lot from it, but here are the things that didn't work for me. Like that's really useful feedback, you know. Or if you just want to say, look, Chicken's great, she's a great lecturer in charge, that'll turn up really funny on this is actually like my employment is based on this kind of stuff. So, but I mean, if I show that students are keen and engaged and they have a story to tell from the subject they've been in, then that's good as well. But please leave us feedback. Super important. It's like you giving to the students in the future, right? If you tell us what's working and what isn't, allows us to shift the way the course runs and stuff like that. Especially right now, because this is the only time that COMP1511 has run entirely online. So your feedback on how this is run online will give us a lot of stuff to compare against the feedback we got when it was run in person. So please fill it out. Shouldn't take too long. I think it's like a 10-15 minute survey. Unless you want to give us a whole lot of information, you can take longer with it if you want. We set aside some time in the labs for the survey, but since the labs aren't quite as structured as they were previously, you may not get a chance to do it there, so just please fill it out when you get the time. Okay, continuing back into some of the technical things that we're looking at. So this follows on from what we were talking about earlier. We got up to pointers. So characters and strings. Characters are not significantly different from integers as a data type. They actually are just 8 bits of integer, so 8 bits of number, but they allow us to encode letters by saying that each number refers to a letter in a certain way. So ASCII is the encoding we generally use to encode characters into 8-bit integers. You don't need to know the ASCII table to be able to use them. You can always look it up if you need to, but it's not super important. And then we looked at strings as well. Strings are arrays of characters, so collections of characters. When we use arrays of fixed length with numbers, it's usually because we need exactly that many numbers to be able to do something. Whereas when we're using an array to store a word, we as humans think of a word as just being an individual concept. But nearly every word, well, not nearly every word, like, you know, heaps of different words have a different number of letters to the other words. So we can't just have a fixed length array that we know can fit all possible words unless we have a really long one. So what we're expecting when we're putting a string array together, so an array of characters together, is that there's going to be some empty space at the end that we're not using that we might use for something else. Because there's often going to be empty space, we use this null terminator. Null terminator is a special character that says, I am the last character that you will look at in this array, and after you see me, the null terminator, you will not read any more letters in this array. So all of the string library functions, all of the printf, scanf with the %s, if they see a null terminator, they will stop there, and they'll stop reading data from beyond that. Someone said dad joke. Taylor. Lovely. I've forgotten a lot about using and storing characters. I hope it's not a character weakness. Okay. We have a lot of library functions for C. Yes, we have a lot of library functions for C. We have a lot of C library functions for strings that make working with strings easier. So this is one of those points where if you want to go in and start looking up the library functions, you can get a lot out of that. So some stuff for strings in code. If I had a hash define somewhere above here that was max length, I could make a string of max length called input, and I could fgets into that. So fgets would say this is the maximum length that I can fill an array of, and I will take it from the standard input. Standard input is what the user's typing into the terminal while the program's running, and then I will store it in this string here, and then after that I can just print it back out. And if I want to, I can do something silly by saying, okay, because it's an array, I could print it out vertically if I want to by putting a new line in between each character that I output. So just some sample code here for working with characters and strings. We then started looking at structures. So we start building things up into more complicated program structures. I'm trying to use the word structures while I'm talking about structs. I mean, it is that. This complexity is only possible after we have a good understanding of the basics. So if we know what stuff like arrays are, if we have a decent idea about how memory works, we've got an idea about how variables work, we can start building custom variables made up of other variables. So before we can use a struct, we will say what the struct is. So we have to give it a name. And so we use the keyword struct, and then we give it a name, and then we say, okay, our structure has these bits and pieces of data in it, and they could be variables of other types. And since the structure is a variable, yes, you can put structures inside structures. We've got a whole series of memes through the entire 10 weeks of the course of me saying that yes, every code construct can basically be put inside itself, which then is going to mean that you can build up these kind of infinite chains of things inside themselves, like the while loop inside the while loop inside the while loop, etc. You can actually call functions from inside functions as well, but that's deeper stuff. We'll look at that later. Well, not with me, probably with another lecturer. So the structs can contain other parts. If we want to access the fields, what we call them inside the structs, we can use the dot. But if we have a pointer to a struct, we use the pointy accessor instead, which is the arrow. So two ways to access what's inside a struct. Either you have the struct itself, or you don't have the struct and it's in memory somewhere and you only have a pointer to a struct. So we use these two different ways of accessing them. So I've got this one here, which is a spaceship. And so the spaceship has a name. Let's assume that there's a hash define for the maximum name length. It has a number of engines and a number of wings. And so I've created this one here. So this is a variable that I've made myself. And I've called it X-Wing. And the X-Wing's name is Red 5. Red 5 has 4 engines and 4 wings. So if anyone here knows Star Wars, this is a quote from Star Wars. Luke Skywalker's X-Wing is called Red 5. Then, if I want to, I could make a pointer to a spaceship struct. So remember, the type of this variable called myShip is everything before it. So struct spaceship is a variable type because we've declared it as a variable type up here. And then the star means it's a pointer to that kind of variable type. So if I can have a pointer to that kind of variable type, I call it, and I say, okay, I give it the address of X-Wing here. Then I will access through the myShip pointer via the arrow, not the dot. The dot is where we have the variable. The arrow is where we're using a pointer to a variable. And we can do the same kind of thing. So the ship takes a hit, maybe I lose an engine and a wing at the same time when that happens. Just some sample code. All right, memory was a big deal. There's a lot of stuff that we think about in memory. Everything that we do with our code is stored somewhere in memory. So all the instructions that we have will be in memory somewhere. All the variables, like we've talked specifically about variables and about their memory locations. So all variables sit in memory also. One thing that we do want to think about is the scope of variables. Scope is a keyword that you will probably hear again later on, where what I like to call the Vegas rule of scope is what goes on inside curly braces stays inside the curly braces. So if you create a variable inside a set of curly braces, once those curly braces shut, once they finish, that variable will not be accessible anywhere else. Its time is over, and it'll be finished. So that means that that variable gets put in memory temporarily and then gets wiped from memory when it's done. If ever we want something to last longer than the curly braces, then we can do some manual memory allocation. So we had the functions malloc and free that would allow us to grab another piece of memory and say, this piece of memory is something that we're going to use, and we don't want any closing brackets out of scope automatic destruction of my variables to happen to this particular one. So it's a piece of memory that I've decided I'm going to use. When I'm finished with it, I can tell you when I'm done, and I can say, okay, free this memory, give it back to the computer can use it for other things now. When we're using malloc, we use size of to say, I have a type for a variable and I would like exactly enough memory to store that particular variable. So there's one line of code that we're going to see a lot, which is this one here. So we've got the same struct, the spaceship. So I went on a spaceship thing for the for this lecture. So when I call malloc, I will say size of struct spaceship. So this is my variable type here. Size of looks at the variable type and says how big it's going to be, and it tells malloc, memory allocation, to give us that much memory. So memory allocation goes through the program's available memory and says, okay, you got a spare spot here. I'm going to take that memory and assign it to you for use, and I will give you a pointer to that memory so that you can keep track of it. So I then need to store the result of malloc in a pointer. So I go, okay, cool. I've got my ship, and my ship is a spaceship pointer, and that's on the other side of the malloc. So this line here is going to look really familiar because basically every time we allocate memory, we're going to do it on a line of code, nearly exactly the same as this. There'll be a type here, and it'll match the type here in the pointer. We'll store the result of malloc in a pointer. And then I can access it by saying, okay, let's copy the Millennium Falcon into the ship's name. It has one engine and no wings. And then let's say I lost my ship in a game of Sabak, so I'm going to free its memory. The ship is free, it's gone. I don't have control over it anymore, so I could free the ship after I've used it. So this is the basics. When it gets deeper, we will get to the idea that sometimes we can allocate lots of little pieces of memory, and freeing them becomes quite complicated. I think that people have a decent understanding of this because you had to do a lot of work with that both in Tutes and Labs and in the second assignment. When we got to a certain point, we had structs and we had pointers and we had memory allocation. That allowed us to start building a new data structure. And this new data structure was linked lists. The beauty of linked lists is they're a struct that contains a pointer to their own type, which means that each one of these nodes in this linked list has a pointer to another node. So at first this would have been confusing because it was like, how can a node point at a node when it's a node itself? And it's like, it's not necessarily pointing at itself, but it's pointing at another one of the same type as itself. So when we have these pointers giving us access to these other nodes, we can chain them together, and then we form this structure called a linked list. Linked lists are useful because you can tell what happens when I try to speak too fast. I'm going to calm myself down and continue. Linked lists are useful because They don't necessarily have a fixed size like arrays. They're not as strict as arrays. They can grow and shrink however you need to insert or remove elements into them. And we can insert or remove elements in between other elements in a linked list without any problems. So if I wanted to insert an element in between these two, I would just allocate memory for it and have this pointer aim at the new item and the new item's pointer aimed at this. I find working with linked lists to be much easier if you draw pictures of them as well, as opposed to arrays where you can kind of keep the idea of an array in your head because there's all these numbers and stuff like that. And Matthew's singing Pineapple Pen there. Yeah. Linked lists get confusing because it's easy for them to kind of, because they're so flexible, it's easy for them to morph into different shapes in a sense. And each one of these nodes is not necessarily next to each other in memory, so they're just in random parts of memory depending on when they were memory allocated. That makes them quite different from an array. An array is like a single block of memory, where each element in the array is right next to the previous one. They'll all be right next to each other, and it'll just be one chunk of memory. Linked lists don't have that guarantee, so they're just kind of everywhere, which also means they're not limited in needing to be right next to each other. Okay, more memes from some of my students. If you remove the first item from the linked list, the second item says, "Yeah, I'm head." Very, very contrived. They had to to color in a lot of that stuff there to make that work. Okay, some code for linked lists. So I'm continuing on my Star Wars theme here. So this time it's locations, and so you might remember working with linked lists of locations. This is not exactly the same thing, but if we had a linked list of locations that were planets, for example, so I've got Tatooine and Yavin 4 here as planets, and I'm building a small linked list by saying this is the head, and it points at the old head, which is null, and then we have add node, we will add a new head, and then it points at the old head there. And so we've got this add node function here, which is going to do our memory allocation for us, and is going to set up the name and the next pointer that we've been given here. So this is just really, really basic linked list code for constructing a linked list. We've gone into great more detail than this, and we've learned how to build linked lists not just by adding a new head every time. We've learned how to add things to the end of the list as well. We've learned how to insert things partway through the list. So I wanted to talk about, oh, there's no space on this slide for my face. I'm just going to put myself here for the moment. I want to talk about some of the details that are going to happen with pointers, structs, and memory, because things get really fiddly when we start using pointers a lot, and it's really easy to forget what pointers are and how they work. So when we think about a pointer is a variable, and it's a variable that stores a number, which means the way that a pointer functions is not that much different from an integer. An integer is a variable that stores a number somewhere in memory. The pointer's number happens to correspond to something else in memory. It happens to be a location in memory that you could actually look at and get some other data from. So the trick is, the pointer being a number, if I change its value, so if I change the value of the pointer itself, that means that that pointer is no longer pointing here in memory, for example, it's pointing here in memory, or it's pointing over here in memory, right? So changing the value of the pointer changes the memory address that it stores, which means that we're making the pointer aim somewhere else. So we need to think about that carefully. This is if we're changing the pointer as a variable on its own. So there's no stars and there's no arrows or anything happening, we're just changing the pointer. So you can see, where are we? Here, where the head pointer, there's no star on it, so we're not looking at the element that's the head, we're looking at the pointer that we're using to aim at the first element, and we're saying you are no longer going to be aimed at null that you were before, you're now going to be aimed at the result of this add node, which is going to be the pointer to the node that was just created, right? So this is me saying I've changed the location that the head is aiming at, and I haven't changed what that variable is, Like I haven't gone to that variable and changed any of the details inside it. What I've done is I've said there are these memory locations that head could point at, and now I'm just moving head to aim at one of those. Now the star and the arrow, they're very similar. They do something different. The star allows us to go to the memory location. So it's like there's a pointer here, and we could change things in the pointer, and that would change where it aims. And the star says go to where it aims, see what's there, and then access it like it's a variable. So the star and the arrow are both very similar. The arrow is a specific case that works with fields of structs. So it says the arrow says we are also going to follow this pointer to whichever struct it's aimed at. Look at one of the fields inside that and see it. Liang's asking why it's called dereferencing. It's because the pointer is a reference to something, and to dereference something is to take it from being a reference to being the actual location. So it's kind of like the dereferencing is traveling from the idea that something is there and then taking it in. By-ref is the idea of passing by reference. That's the idea that we could give a variable to a function, and the function would have access to the original variable. So when we give a pointer to a function, we're basically giving a reference to a variable. When we give a variable to a function, we're only giving the value. So we're not giving access to the original variable, we're just taking the value out of it. Yeah. So the by reference and by value is very, very deep into how pointers and functions work. I'd suggest go back and have a look at how we were talking about putting pointers into functions, because I go into detail there. And also, what Tom's saying there is that some programming languages give inputs into functions as value, and others give input to functions as a reference. So some of them say that any variable that I put into a function gives you access to the original variable. And others, like C, say any variable I put into a function does not give you access to the original variable. It takes a snapshot of the variable's value at that time and gives you that value. So you will actually see this difference. Like some programming languages will say we pass by function by reference, and other programming languages will say we pass by value. So the first one you've learned happens to be C, that passes into functions by value, but there are definitely others that pass in by reference. Yep, I won't go too deep into what's going on in chat. Okay, so the arrow as well is like the star, but specifically with the struct. Oh damn, I left something in there. I'm just going to change this. That was a different assignment. I thought I changed everything that referenced that assignment in this. Anyway, so if we use the arrow, then the other end of the arrow must point at a field that's inside the struct that the pointer is referencing. So the pointer is aimed at a struct, and the arrow says you can follow the pointer into the struct and look at one of the fields inside the struct. So this does a double job where it dereferences the pointer, as in follows the pointer to the location it's looking at, then it looks inside the location and says, okay, let's look at one of the fields inside there. Which means we can do some hilarious things where we could go into one pointer and go into a field inside that, which is another pointer, and then go into a field inside that struct, which is also another pointer, and you can get really deep into these things, and you can still access these things because each one is going to happen one at a time, and we're going to follow this chain of pointers through things. So it's totally possible to have some complicated chains of things. Okay, so let's create a really simple linked list with two locations. So we've got Dantooine gets added first, and then Alderaan gets added next as another location. So I don't know if I don't know how much people people follow the original Star Wars, the original trilogy, but I'm telling a story here. Okay, so let's create another pointer to Alderaan, which is the which then becomes which then copies the head, and then let's set head to be the memory allocation of a new location struct. So we need to think about, if I do this, we need to think about what this actually means. So is this me wiping Alderaan by memory allocating over it? Because the actual node that I created Alderaan, if I malloc with a pointer that's aimed at that, what happens there? But what we need to do for this kind of situation is we need to draw a picture and see what this actually means, because this kind of looks like I'm destroying Alderaan by memory allocating over it. I'm using Alderaan because Dantooine would be too remote to provide an effective demonstration. I hope someone got that. Someone better have got. Anyway, I'm quoting Star Wars for anyone who didn't get that. Okay, so let's look at what this is once we're actually looking at this in code. So we have two linked list nodes, and someone got it. A couple of people got it. Yes. Okay. See, I know that the speedrun got me ahead of time, so now I can actually talk about things. Okay, so we've got the two nodes here that we created. They're linked up together, and we have this head pointer. Then what we said was struct location Alderaan pointer. So there's a pointer called Alderaan is equal to the head. So what does this mean? This means I've created a pointer that is the same as one of the other pointers. If a pointer is the same as another pointer, it means they're aimed at the same object. It doesn't mean they're the same thing. So this is what happens when I do this. Struct location pointer Alderaan is equal to head means I have a new pointer aimed at the head pointer. So I've created a new one that gives me access to this. And so this is the same as me saying, oh, I've got a current pointer that points at the head, and that current pointer is going to move along through the list. So for example, I've just got this one that just identifies this node here as Alderaan, which is good because they're the same name, so that would kind of work. Then I do this thing where the head equals a memory allocation of another location. So what sometimes happens, I really want to talk about this because this can confuse people a lot. What sometimes happens is when you think that this pointer aims at an object already, and then I say memory allocate at that location, it looks like what we're doing is actually blowing up Alderaan. Sorry, just huge spoilers if you haven't seen Star Wars. However, you have had 40 years to see Star Wars. Well, not in general. Those of us who have been alive that long have had 40 years to see Star Wars, but not everyone else has. Okay, so what actually happened here was, instead of this malloc affecting what the head pointer was aimed at, the malloc actually creates a new memory location here, a new struct in memory, and then it changes where the head pointer aims, so the head pointer now aims at this. So the trick is, there's no star and no arrow here. A star or an arrow would have taken us to this node, but since there was no star or arrow, all we changed was where the head was aimed. It was no longer aimed at this node, it's aimed at this new node that's just been created. And we don't know what we're doing with that node yet, but this is an example of how we're like moving pointers around, we're using memory allocation, we've got linked lists, we're copying pointers and stuff like that. And I just wanted to show this because I know that we kind of need to look at these things multiple times to get them to click, and I wanted to show you an example of pointers now that we've got everything else. You know, we've done all of this other work with pointers and linked lists and things, and now we can see, okay, we can actually move these pointers around, we can create new memory allocations, we can copy pointers and things. And hopefully this gets you a little bit closer to a deeper understanding of how pointers work. Nicholas is asking if Starhead would do that. Starhead would do something weird and different here because you can't assign a pointer which is this malloc, to the star head, because the star of the head is another memory location itself, so it's not actually a pointer. You could actually do head next is equal to new thing, and it would create this new one, and it would change where this next pointer aimed. There's no real way that we could go in here and kind of obliterate Alderaan like this, which is why there's no Death Star in this example. Anyway, yeah. Yeah, so what Catherine and Nicholas were asking wouldn't necessarily be able to overwrite Alderaan, because if we did star of head, we couldn't assign the result of malloc to star of head, because star head would be this node, and this node's not a pointer, so we can't override it with a pointer, whereas the output of this is a struct location pointer. Yeah. Leon is asking, can you make a pointer to aim at a pointer? Yes, you can. So each of these pointers, as I said, it's a variable. A pointer is a variable, which means it sits in memory somewhere, which means someone else can point at it. So you can have pointers to pointers. We specifically did not teach pointers to pointers because I want you to learn the basics before you learn the weirdness. So yes, it is possible to have pointers to pointers. It's also possible to have pointers to functions. And we didn't cover any of that because they're fiddly to the point where, like, honestly, we didn't have enough time to continue teaching that. If I was going to keep teaching you for another, like, 10, 15 weeks, we'd probably look at pointers to pointers, we'd look at different structures, we'd look at linked lists with multiple pointers in each node and stuff like that, so we could grow this, but that's for other lecturers. So there are other subjects of other lecturers where you will learn all of that stuff. And we'd go in the other direction as well. So we would go, let's look at memory from a really low level. Let's look at optimizing our use of memory by putting certain things next to each other and stuff like that. So there's all this really cool stuff like that. Yeah, Catherine, what you're seeing there, a pointer to a pointer. So when you think about it, we have used those. argv is a pointer to a pointer because a two-dimensional array is actually a pointer to a pointer in a sense. So we've got a pointer to the two-dimensional array and then a pointer inside that to look at one of the strings inside the two-dimensional array that is argv. So you've kind of seen it, but what we do when we're working with that is we think about it in a different way. We say this is just an array of strings, and it's much easier to think about it as an array of strings rather than a pointer to a pointer of a character, which is super confusing. Okay. So keeping track of pointers can be fiddly, and we were talking a little bit about. Wait, Matthew's saying I'm missing a closing bracket. Where here somewhere? Is it here? Yeah, that's it. There's a closing bracket missing there. I actually don't need this one. Yeah. I don't need that one, which means that my diagram here may have had the same issue. I didn't need to open a bracket around size of because it's the only thing inside the malloc. Okay, let's continue. So, some of your castle defense implementations will have situations where you could have this. A realm follows the castle pointer, follows the next pointer of the castle, and the next pointer in that, and then the pointer to the enemies, and you're like, where are we? This is the kind of thing where you need to draw diagrams if you're going to use anything like this, and I would generally suggest that if you have this many pointers chained up at once, that you've potentially got a problem. You're going to cause yourself a problem with not knowing where you are. It's the same as having overly deep nesting. Once you're overly deep, grabbing multiple pointers like this, you could be in trouble. So, things to remember about pointers. Changing the pointer itself. So if you change the pointer without, the pointer doesn't have an arrow or a star on it, it means it hasn't been dereferenced. You haven't followed it to a memory location. So if you change a pointer on its own, it changes its value, which is a memory address. And that changes where it's aiming. It doesn't do anything to the data that it was at the end that it was aiming at previously. If you use the star, then you're going into the data, and anything you change is changing the data itself, not the pointer. Right. So remembering that difference, that a pointer gives you access to something else, but it is also a variable itself. So sometimes we change a pointer, sometimes we change the thing that the pointer is aiming at. Okay, we're getting near the end. So the last thing that I taught you was abstract data types. And so this is like, see, my students sent me the same meme, but this time they didn't have to block out as much of it. So if I pop the top of the stack, the item at the top of the stack says, I'm a head out. So when we were working with abstract data types, and you've been able to see a decent example of working with abstract data types in the second assignment, we haven't asked you to generally, to like sort of create one from scratch, because this is the kind of thing where we wanted to at least give you a chance to use it, to get some familiarity with the idea of abstraction without having to build it entirely from scratch, because that's like a technical exercise that would take a bit more time. I actually would be reasonably confident that 1511 students, after they've finished the second assignment, will actually be pretty happy in building an abstract data type, because you've seen me do it with the queue, and you've seen an example of using quite a complex one in the second assignment. So what we have is a header file. Header file is the key to how this thing works. So the header file and the implementation file are linked together, and whatever file is going to use the functionality provided is going to include the header file. So the header file is the bridge between two things. This is the same thing that I've been talking about before, right? The bridge, where I could have a main on one side and a C file on the other. They both interact with each other through the header, and the header says these are the specific ways that you can interact, but you cannot cross over into the other file and make changes or do anything strange. So this means that the implementation in the C file doesn't have to be known by the main file or whatever other file is using that library. In a sense, it's the same as any of the functions that we've been using in the C libraries. All of those functions we've been using, we don't know how they're written and we don't know what their underlying structure is, but we use them just because we trust them. So what we get is that we can only use those functions, which means we cannot access the raw data, which means we cannot accidentally access the raw data incorrectly. So for example, something like a queue, we can't insert an element into the queue anywhere in the queue where we want it to be. The rules for the queue, the abstract rules for the queue, stated that anything that was new had to be at the end of the queue. And so what we did was we made sure that if someone wanted to add something to the queue, they call the function, then the C file implements it. So the C file says, I'm going to organize everything that you've put into the queue so that they remain in an order, so that anything you take from the queue is guaranteed to always be the oldest thing that was in the queue. This means that we trust the C file to follow the rules when we use it in the main file, and it also means that there's just a limited set of things that we can do. There's only a few functions we can call from the main file. We don't have to think about everything that's in the C file. We don't have to think about what are the ramifications of this being a linked list versus this being an array. Do I have to act differently? No, I don't have to act differently. My main file will work regardless, because we've agreed in the H file how these things are going to cross over. You'll notice that in your assignment as well. All of your assignments have different C files from each other. Yet our one main file that we've provided for you will be able to access everything that you've implemented, assuming that you've implemented everything correctly following the rules that are agreed upon in the H file. SK is asking about a pointer pointing to itself. Yeah, it's technically possible to have a pointer pointing to itself. And I don't think it's even going to break anything. An infinite linked list where something's node pointer aims at itself, so it never ends because it just keeps going back to the same data. I think that there would be a use for that somewhere, somehow, but I'm not sure exactly what. Okay, so some information about the abstract data types. So we have a ship internals. the type def here allows us to, in a sense, create a new type so that we don't get caught up thinking about this thing as a struct pointer. We get to thinking about it as an abstract thing instead. So I can create a ship, I can free a ship, or I can send a ship on a voyage of a certain number of years. I probably shouldn't have had the variable name the same as the type name here. This is potentially going to confuse people. But we'll leave it for the moment. This is just a lecture example. So the implementation inside may have a ship internals, which is this structure, and the main file that's using it will never know what this is. It will never get access to it. It will only have this capital S ship and know that it can use it with certain functions. So I've got this thing that will create a new ship by memory allocating it. And then freeing it. I'm missing a line of code here. I think I should also be doing, because I was given a name, I should probably string copy the new ship's name with the name that I was given. Alright, just going to do that. I've gone off the bottom of my slide here, but it'll be fine. Okay, so I've got the ability to create the ship, free the ship, and set it off on a voyage. So it gets discoveries every year that it goes. I'm just making this stuff up, right? This is not super important. I'm just showing that there might be other functions that we would implement in the C file. So when we use this in our main, we would include the ship.h. Including the ship.h gives us access to these functions and this capital S ship that we can use, which means if we want to make a ship, we go call the new ship function. Is it even called new ship? It's called ship create. I don't know how that ended up like that. So we create this ship called the Enterprise. So yes, I'm jumping to a different sci-fi ship universe now just for fun. And I say go on a voyage, which was also here, of 5 years. So the Enterprise goes off on its 5-year voyage to seek out new life and new civilizations. Anyway, so this is us using an abstract data type. The H file gives both sides of the abstract data type a kind of blueprint for how they're going to do things. So the C file is going to say, these functions, I must run these functions, so I have to do all the details underneath. And the main says, these are the functions that are available to me. I can call these functions if I want to do particular things. These obviously get much more complicated than this. I did a really small example so it could fit on the slides, and it still didn't fit exactly on the slides. Okay. So that is us, and we are now, I'm going to move my head here. I'm going to be the smart one, even though I've never coded with blocks in Minecraft. So now we're programming. Now we've hit a point where everyone who has done this course has reached a point where they have at least some understanding of what programming is. And so I just love these memes. They're great. Not sure, I mean, like the not great because the English grammar, there's a syntax error in the English code here, but because there isn't a logical error, us as humans can still compile this. Not sure if I'm good at programming or good at Googling. That'll happen. It's actually pretty standard industry practice that we Google a lot of stuff while we're programming. It's not that bad. And then also we've got this hilarious big brain meme here of just coding in things. I don't know if people have done Scratch before, or coding with command blocks in Minecraft. So you need galaxy, massive galaxy entity brain existence to be able to do this. I'm not sure if these are in the right order, because I think coding in Python is actually easier than coding in C. But anyway. So, where do we go from here? There's so much that you now know. There's so much you can now do with code that you couldn't necessarily do before. But there's also so much more that we're getting to. There's so much more to learn about programming. What I like to say to people who are like kicking off their journey into programming as you are now, I mean, some of you are kicking off your journey into programming, some of you have already committed to it years ago, and this is just another step on the path. For some people, this is the beginning. Um, when we look at the number of research papers that are being published in the world of computer science every year, it's actually impossible for any individual to read all of these, let alone understand them. Just read them. You wouldn't have enough time to read them all, which means that the field of computing is active and moving in a way that we could never keep up with all of it. So if you want to turn learning into programming um, into a lifelong pursuit, then it is there for you. It is available. You can totally do that. So there's always something there that you can find. There's always something there that you can work on. There's always something new that someone can hold up and go, hey, do you want to learn about this? And you're like, oh, maybe. That sounds interesting. And I hope that if you look back at what you knew about programming at the start of the term and what you knew now, like, we escalated, right? So we taught you some things and then we escalated and we pushed you to learn about, complex data structures and memory management. We took you inside a computer and said, okay, this is like the theoretical model, like the Turing machine of what a computer is and this kind of stuff. I hope that everyone is sitting at a point now where even if you're at a point where you think you're going to fail the course, you still know heaps more about the world of computer science and programming than you did before. So what you get to now, I think, is you can decide what you want to do from here, because what you can learn about programming, because there's so much to learn, what you can learn about programming now is based entirely on how much commitment you want to give to it. And I know some of you there have already signed up in a sense. I know some of you there have signed up and said, this is the life I want to live. I want to know everything. I want to deep dive into this. Some of you are thinking, okay, coding is interesting and that's cool, but this isn't something that I need in my life. So I'm glad I knew about it, but I've got other things that I want to do. So it's up to you. You learn however much you want based on how much you commit to wanting to learn. And so I want to leave you with this kind of message that more than what you know now, more than what I've taught you, more than whether you can work with linked lists and pointers, and whether you fully understand how memory works in a computer, or what a stack and a queue is and all this kind of stuff. What I hope that you've gotten out of COMP1511 is knowing the difference between caring about what you're doing and not, and knowing that if you do put the time and effort into this, it doesn't matter where you're at now. It only matters about where you want to be in the future and figuring out how you're going to get there, because I think that's the most important thing. So don't worry if things are not working out in the moment. Sometimes stuff not working out of the moment is where we learn the greatest lessons. So I want you all to look after yourselves. I want you to look after each other if you can, as much as you can. I think there's not enough of people looking after each other in the world right now. And to enjoy what you do, because I think you're at a moment where you can absorb so much from the world. You can absorb so much information, and it's a really wonderful thing. So I hope that you will enjoy what you do, whether it is continuing with computing or not. And I hope you'll be fulfilled by whatever it is you choose to do. And I look forward to hearing about what you've done in the future, and to bask in the reflected glory of your successes as they happen. So yeah, good luck, have fun, do great things if you want to, do anything else that you want to, if you don't want to do great things and you just want to do interesting things. Um, Thank you for spending all the time with me this term, even though we didn't get to spend any time in person. It's been a fun ride, um, and yeah, that was Comp1511. I will I will still see everyone a little bit. I mean, I may talk to some of you during the exam because I'll be monitoring the email address a little bit. I will see some of you next week because there's going to be some revision sessions. I will probably run a separate session to the tutorial revision sessions as well, so I will still see you again. And I really, really hope that when we can start physically going to campus again, that we will potentially be able to run into each other. And I apologize because I won't know who you are because I haven't seen any of your faces in person. And that's a massive shame, I feel, compared to how this would normally be, where I would run into people on campus and I'd say, I've seen that face before in a lecture theatre and stuff. And then someone will come up and say hi and go, hey, Mark, I took your Comp1511 in this term and you know, it was fun to learn from and whatever you want to say, you know. Oh, hang on. I should find Chicken so that she could say goodbye as well. So if we end up back on campus and you do see me around, because you know my face but I don't know yours, unfortunately, please come and say hi, because I would love to at least be able to say a few words to each of the people that we've taught here. I think it's been um, it's just been a fun journey, you know, like, and it's been weird as well because I don't usually do this like here in my own house just talking to a camera. Usually, like, I get a lot more out of talking to you as people. So everyone in chat and stuff, I'm seeing that. Thank you very much. Thank you for your thanks, for everyone who's. I'm gonna um I'm going to go through and read all of your messages there. It's been really nice, to have such a dedicated group of people who have been working so hard at everything, and I've pushed you I've pushed you through some serious amount of content, and I'm really proud of how people have committed themselves to learning as much of it as they could. So it's been a really wonderful experience. Um, Give me a second. Give me a second. I will go find Chicken so that you can say goodbye to her as well. Oh, hello. She sort of tried to run away when I picked her up. Goodbye, Chicken. Do you want to say goodbye to everyone? Goodbye. She's waving goodbye. Goodbye, all. All right. I should say also, this is not the last time you're going to see me. I'm going to try to do more random live stream events. So the last random live stream that I did with Daniel Mansfield, we were discussing one of my ex-students who then turned up in chat. So I since got in contact with her and we had a little chat. And so I think what I want to do is do a live stream sometime, maybe in the holidays, where I actually interview her about what it's been like for her going through a computing degree and then continuing on afterwards, and the work that she's done since, and the stuff that got her all the way to the point where she won Young Woman of the Year in New South Wales this year. Was this year or last year? I think it was this year and stuff. And so I think Women in Tech were really interested. They interviewed her as well, and so I thought it would be really fun for a lot of students to see. So it's not the last time you're going to see me. And I will be potentially teaching other subjects in CSE as well. I'm just going to leave that little thing there. I can't say what it is, I can't spoil it, but there's a potential in the future that you will see me in other subjects. Okay. Thank you, everyone. And yeah, I uh, I really don't know how to end this. um, yes. Well, I think we're done. Wow, Qwerty's transferring to CompSci. That always makes me feel good because I get to that point. I go, oh, I've convinced people to come along, and that's great. Okay, I'm gonna wrap it up here. Um, I'm gonna sign off the help session with Dean. I think it's with Dean, right? He's usually the 6 p.m. one. Is starting up now, so if you need to ask him any questions, last minute assignment questions, now's a good time. Um, Thank you all for coming, and I hope to see you all again soon. Goodbye. Well, I mean, like, I'm streaming again next week, so see you in a couple of days, but Oh, Dean's not going to be there tonight, so someone else is taking it tonight. Alright, cool. Alright, I'm gonna head out.